Today we're going to take a look at section 12.3, which is velocity and acceleration. And mostly it's just a continuation of what we had done last time when we were talking about derivatives and antiderivatives. So we're going to take application to that. So first, a definition: if x and y are twice differentiable functions of t, and r is a vector valued function given by our standard expression for r, then the velocity and acceleration and speed at time t are as follows. So the velocity is the derivative of our vector valued function r, so r prime of t, and it's x prime of ti, y prime of tj, and z prime of tk. Acceleration, same thing, but it's the second derivative of each of those components. And then speed is the magnitude of velocity. So the magnitude of v of t or the magnitude of r prime of t. And that is the square root of each of the components squared. So the square root of x prime t squared plus y prime t squared plus z prime t squared. So what we're going to do is we're actually going to find those different quantities for some vectors. So the first vector we're looking at is trigonometric. It's 2 cosine ti plus 2 sine tj, and it's at the point square root 2. So the square root 2 will come into play in part B. Part A wants us to simply find the velocity, speed, and acceleration. So the velocity would be the derivative of our r equation, right? So the derivative of 2 cosine t is negative 2 sine t, I. And the derivative of 2 sine t is 2 cosine t, and that's j. The speed for this is the square root of each of these components squared. So negative 2 sine of t squared plus 2 cosine of t squared. And hopefully you're starting looking at that and you're thinking, this looks like a Pythagorean identity. It is. If you square each component, they'll have a 4 in them. And then if we factor that 4 out, we have sine squared of t plus the cosine of squared of t, which of course is equal to 1. So this is just the square root of 4, or 2. And then our acceleration vector is the derivative of the velocity vector. So the derivative of negative 2 sine t is negative 2 cosine of t, that's I. And then we have the derivative of 2 cosine of t, which is negative 2 sine of tj. Part B is something we've seen an application of before when we were working at this idea of parametric equations. We wanted to evaluate the velocity and acceleration vectors at the given point. But the point that we're given is actually an xy ordered pair. It's not a value for t. So that's the first thing we actually have to do, is to figure out what value it is for t that we're talking about. So we want our x value, which is 2 cosine of t, to equal square root of 2. And we want our y component, which is 2 sine of t, to also equal square root of 2. If we do just a little bit of simplification, this is just telling us that the cosine value needs to be square root 2 over 2, and the sine value also needs to be square root 2 over 2. Now this one is fairly straightforward to sort of make amends to the fact that these two equations need to coexist at the same time, and they result in giving us a pi over 4 value for t. If that weren't the case, then we would have to list out whatever the t values are that would work, and we would look for one that coincides. So this value, pi over 4, will work. So we're finding the velocity at pi over 4, because that's the corresponding t value to the point square root 2 over 2. So this is negative 2 sine of pi over 4 I plus 2 cosine of pi over 4 j. So obviously sine of pi over 4 is square root 2 over 2, and so I have negative 2 times square root 2 over 2 I, and I have the same thing, 2 square root 2 over 2 j. And this will simplify then, of course, to negative square root 2 I and plus square root 2 j. So this is our first one. The other one is acceleration at pi over 4. Super similar, right? So we're putting this into the acceleration vector, so negative 2 cosine of pi over 4 I, and positive 2, is it positive? No, it's negative, sorry, negative 2 sine of pi over 4 j. So just as before, cosine square root of pi over 4 is going to be square root 2 over 2, and I've multiplied by the negative 2 at the beginning. It'll cancel with the 2 in the denominator. So again, the same thing will happen over here, square root 2 over 2 j. So when we simplify this, actually let me make this just a tiny bit smaller so I can fit it all in there. Okay. When I fit this in there, this is negative square root 2i. And it's negative square root 2j. And you might be thinking, well, that looks a lot like the one before. It does. The signs are the only things that are different on this one. Let's take a look at another one. Number 2, we've got a different vector. This one's polynomial in nature instead of being trigonometric in nature. And it wants us to find, again, velocity, speed, and acceleration. So velocity is taking the derivatives, right? So the derivative of 3t would be 3i. Derivative of tj would be 1j, so just j. And then the derivative of 1/4 t squared would be 1/2 t, and then it's k. So speed is the magnitude of v. Sorry, this really should say v of t. There we go. And so we're going to have the square root of 3 squared plus 1 squared plus 1/2 t quantity squared. Okay, so both the first components are just numbers. 3 squared is 9, 1 squared is 1, so this is the square root of 10. And then the 1/2 t squared would simplify to 1/4, and then it would be t squared, and all that's underneath the radical. So that's our speed. And then our acceleration is taking the derivative of velocity. So there's actually no i's, there's no j's. And then as far as k is concerned, I will now have a 1/2 k. So you can write it like that, that's okay. It's not necessary that you write all those components out, since the only one that matters or has a non-zero coefficient is the third one. So you could also just write it like this. Okay, so now it wants us to take the velocity and acceleration vectors and evaluate them at t. So t is equal to 2 up here, so we don't have to actually search for it this time. But we're finding the velocity at 2. So the 3, and it stays, right? It's just a constant for the coefficients of I and j. But for the coefficient of k, it's different. So k has 1/2 t, so it's 1/2 times 2k. So I end up with 3i plus j plus k. And then for my acceleration vector, evaluated at 2, I actually don't have anything to put it into, right? Like the acceleration vector is actually already 0, 0, 1/2, so there's no evaluation, so it's just 1/2 k. All right, last one. This one is sort of working reverse. We're given the acceleration vector, and we're given some initial conditions, and we're asked to actually find the velocity and position vectors. So it'll feel somewhat similar to something we'd done a couple days ago. We're taking the antiderivative of this, so the antiderivative of t would be 1/2 t squared, and that's the j component. So I skipped over I. My apologies. So the I component actually would have c1 times I. So some constant. The j component would also have another c value, so I'm going to call it c2, and then we'll call it times j. And then we have a similar feature for k, which is going to be 1/2 t squared plus c3. Okay. Now, I actually want to find the c1, c2, c3 values, and I can do that. I do that by actually evaluating in, oh, this is not A. I definitely did not write that right. This is the velocity that we're finding. Please fix that in your notes if you were copying those down with me. We're actually evaluating this at the value that they tell us. So it tells us above that v of 1 is 5j. So this is v of 1, which means I put a 1 where all of my t's are. So this is c1i plus, and we're putting a 1 in, so this is 1/2 plus c2j plus, and again, put the number 2 in. So 2 squared is 4, so this is giving me a, sorry, I didn't mean 2 squared is 4. I meant 1 squared is 1 times my 1/2, so I'm getting a 1/2. Plus the c3k. And this is supposed to equal the vector 5j. In other words, the component for I is 0, so c1 is 0. The component for j is 5, so this is 1/2 plus c2 is equal to 5. So that tells us that c2 is 9/5. I'm sorry, 9/2 is what I meant to say. And then c3 is that the 1/2 plus c3 has to equal, again, 0. So that tells us that c3 is 1/2. Negative 1/2, there we go. So my actual velocity vector that I found here is 0i, feel free to not write that component if you wish, plus 1/2 t squared plus 9/2 t, j rather, there we go. And then plus 1/2 t squared minus 1/2, and that's k. Okay, and then we're trying to get back to the position vector, the r of t equation, right? So we'll do the same thing again. So once again, I do an antiderivative here. It's going to be a c1i. In the middle here, that 1/2 is going to get divided by 3, so this is now going to be 1/6 t to the third, plus 9/2 t now. Oopsie, almost forgot my plus c, plus c2. And then plus, and so now we're going to have 1/2, again divided by 3, so it's 1/6 t squared minus 1/2 t plus c3. And this is actually c3k. I forgot the j here. There we go. J and then k. All right, good deal. And this is supposed to equal, well, when I plug in the number 1, right, it's supposed to equal 0. So this is the r prime now of 1. So it's going to be c1i, that's fine. When I have 1/6 plus 9/2, that's what's going on there. I end up with 1/6 plus 9/2 is 14/3. I don't know why I have those parentheses on there. Let's take those off. That's j. And then we have the same thing, the 1/6. Now it's minus 0.5. That's negative 1/3. For k. And again, I plugged in the number 1, and it says it's supposed to equal the 0 vector. So each component would equal 0, so c1 is 0. 14/3. Ooh, I left off the plus. Let me put that in there. I left off my c value here. That's why I needed the parenthesis. That's what I had forgotten about. c2j, and the same thing happens over here. c3. Okay, so the 14/3 plus the c2 have to equal 0. That tells us that c2 is equal to negative 14/3. And the k component, excuse me, is the negative 1/3 plus c3. It's also supposed to equal 0 because this is 0 vector, excuse me, that we're doing. So the c3 is actually equal to 1/3. So ultimately, our r equation, our vector value function equation would look something like this, where we have r of t equals, feel free to write the 0i or just leave the 0i off, right, as being 0, plus 1/6t cubed, plus 9/2 ct, and then we found out c2 is negative 14, so it's minus 14/3. We're almost done. That one's j. And then lastly is my k value. So the k value is supposed to start out with 1/2 t squared, 1/2 t squared, and then, sorry, that was I got the wrong line, 1/6 t squared, c squared, yeah, 1/6 t squared, and then c cubed, there we go, t cubed, okay, I actually had a typo way back up there, so it's 1/6 t cubed, so this is 1/6 t cubed minus 1/2 t, and then we've got the c value, which is actually a 1/3, so plus 1/3, and that's the k component.